This audiobook of the original America Burning was produced by the firefighter podcast Combustible. More details on this project can be found online at www.combustiblethepodcast.com. The audio for this recording is consistent with all copyright rights and permissions associated with America Burning and is not affiliated with or endorsed in any way by the federal government or the U.S. Fire Administration. Chapter 7. Equipping the Firefighter. Of the fire chiefs and firefighters who responded to our nationwide survey early in 1972, more than 7 out of 10 said there is a need for greater innovation to improve the equipment and protective clothing they use every day. And no wonder. A quick glimpse at firefighting practices yields a sampling of where improvements can be made. The breathing apparatus designed for 30 minutes use typically weighs 30 pounds. Often firefighters reach exhaustion long before their 30 minutes are up. The weight of the apparatus, it seems likely, contributes to the exhaustion. In actual use, moreover, a 30-minute apparatus often provides less than 20 minutes protection because great exertion requires more air. Most firefighters' helmets readily conduct heat to the inside of the helmet. Beyond certain temperatures, helmets made of hard plastics lose strength and begin to deform. Helmets and breathing apparatus alike tend to get snagged by protruding objects. In many instances, firemen wearing face masks cannot put on their helmets. The two don't fit together. Turnout coats can be virtual sweat boxes, even when there are air vents under the arms. To the extent that turnout coats hinder body movements or build up body heat, they contribute to firefighters' exhaustion. A fireman manipulating the controls of an aerial ladder must peer upward many stories to see how to guide the ladder into position. If the smoke is too thick to see through, he must have another firefighter perched precariously at the top of the ladder giving him instructions as he swings the ladder into position. As Howard W. Emmons, professor of mechanical engineering at Harvard, pointed out in 1968, a man in Houston, Texas can manipulate a spaceship photographing the moon, but the fireman must climb up to the top of a 100-foot ladder to find out just where it is. These and many other deficiencies have been around for years, despite the great power of American ingenuity to innovate to overcome technological problems. Few equipment manufacturers can afford to invest heavily in research and development, especially when the payoff in a fragmented and conservative market is so uncertain. Marketing is affected by the fact that many fire departments simply cannot afford to buy innovative equipment. Others purchase conservatively because they lack the technical expertise to evaluate innovative equipment. Because firemen typically spend their careers with one department, they become attached to the tried and true methods of that department. Of course, the fire services are not alone in facing barriers to innovation. In recent years, there has been growing recognition that the innovative process, by which needs get translated into research and development projects, and the results of research and development get translated into new products or processes, throughout American society can be improved. In his message on science and technology in March 1972, the President assigned the National Science Foundation and the National Bureau of Standards responsibilities for finding ways to spur innovation. In response, the National Science Foundation established an experimental research and development incentives program to seek ways of increasing the efficiency and speed of conversion of research and development to new or improved products, processes, and services. The National Bureau of Standards launched a similar effort, called the Experimental Technology Incentives Program. The blockages to innovation in the fire services are many, and they offer a rich vein for scientific prospectors. Moreover, the blockages together form a major impediment to improvements in the quality of life, which the National Science Foundation lists foremost among the kinds of innovations to be spurred along. The Commission urges the National Science Foundation in its Experimental Research and Development Incentives Program and the National Bureau of Standards in its Experimental Technology Incentives Program to give high priority to the needs of the fire services. Guidelines for Research and Development. The fire services do not need innovation for the sake of innovation, the way car manufacturers need styling changes to assure themselves new customers. The fire services need innovations in equipment to improve their performance. Improved performance, in turn, can mean any of the four following: saving more lives, reducing deaths and injuries to firefighters, reducing property losses, and protecting the public at lower cost. Clearly, reducing life loss, reducing firefighter injuries, and reducing property losses are prime considerations. Improvements in these areas can be made simultaneously. A firefighter better protected against injury to himself is, of course, better equipped to suppress fires and rescue people. No technological innovations designed to reduce life and property losses should create new risks to firefighters. In all research and development efforts, then, effectiveness in lowering firefighter injuries, as well as life and property losses, should rank ahead of dollar savings as a goal. Current technology, for example, makes feasible automated control of hose pressure at the scene of a fire and could free an additional fireman, the one now operating the controls on the truck manually, for service at the nozzle end of a hose. Yet, the job of the man on the pumper is a complicated one. He must see to it that men holding a hose line do not get thrown by surges in pressure caused by unequal demands from different hose lines. He must cut water pressure when crews are endangered by ladder sway and cut pressure when hoses rupture. He must act as a relief man for crews, a reserve for rescue of fire victims, and a protector of the pumper from vandalism. An automated system that left any of these protective functions unprovided would be an unacceptable substitute. A second requirement of research and development is that they stem from an accurate assessment of fire service needs. Almost any piece of fire apparatus, for example, can be built bigger, better, and more expensive, with a greater capacity to perform its expected functions and impress the citizenry. But in the real world of tight fire department budgets, trade-offs are needed. Thus, the chief emphasis in the development of improved firefighting equipment should be on apparatus designed to meet most potential fire situations, rather than on equipment rarely needed. More research is also needed to help settle questions of diversity versus standardization. Standardization of fire engine components is desirable from the standpoint of bringing down costs. Diversity may be needed to meet the varying needs of different communities. The best solutions may lie in the middle, that is, with standard modules that permit add-on features. One fire department need that should not be subjected to trade-off or compromise is safety. A two-step program of research is needed to identify features of firefighting equipment that do not adequately protect firemen, then to explore means of providing such protection. Thirdly, research and development must take whole systems, rather than piecemeal, approaches. The complete firefighter's uniform consists of turnout coat, trousers, boots, breathing apparatus, gloves, and helmet. It may also consist of a walkie-talkie radio strapped to the body and a handheld flashlight. Each of these elements has been designed separately without thought to its relation to other parts of the uniform. One result has already been cited: a breathing apparatus so incompatible with the helmet that the two cannot be worn together, whereas a face mask and helmet could be an integrated unit. Turnout coat, trousers, and boots are separate items that take time to don, whereas they could be replaced by a one-piece zip-up suit. Walkie-talkies and flashlights are cumbersome appendages, whereas both could be integrated into the helmet. A further example: only the helmet is designed to protect against impact injuries, and that very inadequately, whereas many impact injuries occur on the trunk of the body. Much of the technology exists for better protective gear. Ideally, product development of an integrated system, not unlike the life support system built into the individually tailored astronaut suits, would afford optimum protection. On the other hand, the hard realities of costs and ready availability of the equipment must be considered in approaching the ideal. The National Aeronautics and Space Administration, in fact, has put its space exploration capabilities to work on the problems of developing better breathing apparatus and better protective clothing for firefighters. As for helmets with built-in communication systems, they have long been in use by fighter pilots. To provide protection for impact injuries, technology might be borrowed from bulletproof vests, or even from football players' protective gear. At the same time, research and development are needed to make incremental improvements in existing kinds of equipment. The search for major departures from existing equipment based on a systems approach should not be pursued at the expense of development of improvements in traditional equipment. There are two reasons for this. First, the search for major departures is a long-term investment, and results are not likely to reach the market for several years to come. Secondly, fire departments cannot afford to discard all the equipment they have now, and adoption of major departures will be a slow process, extending over many years. Better versions of current types of equipment will be needed for some time to come. A single example will suffice. Tests of 6 types of turnout coats by the Boston Fire Department have shown that, in each case, the material fails the flammability test for drapery fabrics used in places of public assembly. That more firefighters' coats do not catch fire is due largely to the fact that the heat on the fireman's exposed hands and face drives him from the flames before his coat is endangered. If hands and face can be adequately protected, and the technology exists to do just that, then there will have to be a corresponding improvement in the flame resistance of turnout coats. A fifth consideration for research and development: improvements must be acceptable to fire departments. Barriers to acceptance of an innovation are of several kinds. A new piece of equipment may be too expensive in absolute terms, simply beyond a fire department's budget. It may be too expensive in relative terms, that is, offer too little improvement in performance for the investment required. It may require skilled operators, which fire departments are unable to provide without further training. There can be psychological barriers as well. If an innovation departs too radically from traditional practice, it will be resisted. A related consideration is that developed products need to be adapted to users' capabilities. Human factors engineering, that is, the modification of equipment design so that the equipment is comfortable, safe, and easy to use, has been applied with success to military and industrial equipment, but never, to our knowledge, to fire trucks and other firefighting equipment. A purchaser of fire equipment must be able to make comparisons among different pieces of equipment competing for his dollars. This means that names for particular kinds of equipment, descriptions of their functions, and measurements of their capacities should be uniform throughout the fire protection field. While some standardization exists, confusing discrepancies are commonplace. One result of these discrepancies is that data cannot be compared across different fire jurisdictions. For example, a rescue truck is an ambulance in some places, a pickup that carries firefighters' rescue equipment in another. The National Fire Protection Association has published many standards for fire equipment and an excellent guide called Fire Terminology. But long-established traditions and local custom have not given way totally to NFPA standards. The Commission recommends that the proposed United States Fire Administration review current practices in terminology, symbols, and equipment descriptions and seek to introduce standardization where it is lacking. Equipment R&D, reducing fire losses. Research and development priorities ought to stem from careful assessment of the needs of the fire services. We can only suggest, therefore, not define, areas where research would be useful. The following discussion is a mixture of subjects on which little or no research is being done, subjects on which progress is being made, and, indeed, subjects in which demonstration projects have already proved successful. Notification. The beginning step in a fire department's effort to put out a fire is notification of the fire's whereabouts, usually by telephone or alarm. Systems exist which sense smoke, products of combustion, heat, or water flow in an activated sprinkler system, and notify the fire department automatically. Improvements in the technology of such systems, especially in bringing down their cost, might encourage more widespread use. Systems based on human activation might be developed which, 1. Meet the criterion of universal acceptability as private telephones do in many communities, and, at the same time, 2. Discourage false alarms, which account for a third of the fire calls in many cities, and 3. Provide for the transmittal of qualitative information about the fire. Some cities are already using public telephones which require no coins for emergency calls. These telephones, if adequately maintained against breakdowns and vandalism, together with private telephones, would substitute for fire alarm boxes. Response. Computerized systems for dispatching firefighters and fire trucks have been installed in a number of cities. Into such systems are being built retrieval mechanisms that transmit to firefighters floor plans and other helpful information about the building on fire. Suppression. Lights, periscopes, or closed-circuit TV might be mounted atop aerial ladders. Sensors to locate trapped victims and chemical detectors to warn of dangerous concentrations of toxic gases are other possibilities. Infrared sensing devices are available that can locate fires in smoke-filled rooms and fires inside walls, but they need development and demonstration of their usefulness to the fire services. More research is needed on extinguishing agents, hardware, and techniques to improve the effectiveness of existing agents and to investigate the chemical and physical mechanisms of new agents. Water, particularly in its droplet or stream state, requires further study. There is a controversy, for example, as to whether keeping buildings closed and applying water fog is a suitable alternative to ventilating the fire and attacking with water streams. Additives that reduce friction losses in hoses have proved their effectiveness but are not widely used. Foams and dry chemicals have proved their effectiveness and are being continually improved, but exactly how these agents operate to extinguish fire is little understood. More important, lack of knowledge in flame chemistry inhibits progress toward radical departures from present extinguishing methods, such as the use of sound waves. Lastly, Development efforts should be directed toward reducing the weight of suppression equipment, especially hoses and couplings. Equipment R&D, reducing firefighter injuries. Especially in the realm of fire suppression, technological improvements which reduce firefighter injuries will improve the effectiveness of fire departments in saving lives and reducing property losses. Such improvements are worthy of pursuit in their own right, since the risks we currently ask firefighters to take are unconscionable. In many cases, we must assume, the proper protective equipment is not available to firefighters, or if available, is not being worn. When firefighters do not wear equipment because it is cumbersome or uncomfortable, that is to some extent an indictment of the equipment. Toxic fumes. The inadequacy of breathing apparatus systems is shown by studies which indicate that face masks used by fire departments leak to some extent. The National Bureau of Standards has proposed a program of research to improve breathing apparatus systems, taking into account the physiological, human factors, and engineering elements important to their design. The Commission urges rapid implementation of a program to improve breathing apparatus systems and expansion of the program's scope where appropriate. Impact injuries. The only standard piece of equipment meant to protect against injuries from falling objects or other blows is the helmet. The most common standard, which many helmets fail to meet, is resistance against 40 foot-pounds of impact. The British standard is 3 times as high. No attention has been paid to impact protection in turnout coats, despite a Bureau of Labor Statistics study which shows that impact injuries to the trunk occur 26 times as often as trunk burn injuries. Overexertion. While the very nature of firefighting invites overexertion, there are technological improvements that undoubtedly would reduce instances of overexertion. Protective gear could be improved from the standpoint of weight and freedom of bodily movement. In addition, lightweight power tools, for example for prying open doors or cutting through walls, would also reduce the need for physical exertion. Strains and sprains. Lightweight power tools would likely reduce strains as well. In addition, failure to apply human factors engineering to the design of firefighting equipment has led to strains and sprains, as it has to overexertion and other kinds of casualties. What is needed for these and other classes of injuries is thorough study of the kinds of movements and stresses the body sustains in firefighting. Heat and burns. Equipment that leaves any part of the body exposed or which is easily ignited openly invites burns and heat injuries. Development of protective clothing to reduce these hazards should be accompanied by the development of sensing devices that can warn the firefighter when surrounding temperatures are getting dangerous. Getting on with the job. The foregoing discussion is hardly exhaustive. There needs to be undertaken a definitive study of the needs of the fire services. Such a study would have to do more than aggregate what fire departments say they want. It would have to identify needs growing out of demonstrable shortcomings of current equipment. The Commission recommends that the proposed U.S. Fire Administration undertake a continuing study of equipment needs of the fire services, monitor research and development in progress, encourage needed research and development, disseminate results, and provide grants to fire departments for equipment procurement to stimulate innovation in equipment design. As an interim measure, pending establishment of a U.S. Fire Administration, the Commission urges the Joint Council of National Fire Service Organizations to sponsor a study to identify shortcomings of firefighting equipment and the kinds of research, development, or technology transfer that can overcome the deficiencies. Funding would be appropriately sought from the National Science Foundation or from the Department of Commerce under the provisions of the Fire Research and Safety Act of 1968. Capabilities for research and development to improve the effectiveness of the fire services lie in many places: universities, federal agencies, nonprofit research firms, and the fire equipment industry. Research and development in these places will be useful if they are guided by clearly identified needs of the fire services.